In this video, we're going to talk about what it means for a linear transformation to be onto and what it means for it to be one-to-one, and how these terms are related to matrices. Okay, so I'm going to begin with some context. So if A is an m by n matrix, we can associate it with a linear transformation, which we've called T sub A before. And T sub A has domain Rn and codomain Rm. That means I plug in vectors into it that have n entries, and I get out vectors that have m entries. Okay, so this transformation has an input x, and it outputs the same thing as what we'd get as if we multiplied x by the matrix A. Okay, so we've talked before in an earlier video in this section about range of something, so the range of A, but I want to define it a little bit more formally. So the range of a transformation, or in this case I'm saying the range of the matrix, is the image of all of the inputs. So the image of everything I'm allowed to plug in under this transformation. So it's sort of saying, okay, when I plug in everything in the domain into my function, or when I multiply everything by A, what are all possible things? What are all the things that I actually get out? Okay, so what I want to know is what every single output could be. So the outputs look like this, A times X. But we know that A times X they're always going to be linear combinations of the columns of A. So we want to know all linear combinations of A1, comma, dot, 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 up until AN. Because that's what the outputs are. The outputs are linear combinations of them. Okay, so another way to say that more concisely is that's the same thing as saying the span of A1, comma, dot, 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 up until AN. Okay, so the range of a matrix is the same thing as the span of its columns. Okay, so the next thing I want to do is I want to revisit a picture that we've drawn before. So in this picture, the inputs, the things that we plug in, live in Rn. They're vectors that have n entries. Okay, so all of the vectors that we plug in, like x, get mapped to things in the codomain. So I've drawn A times x here as something that I get out in the codomain. And everything that I've drawn in red represents the range in my picture, the range of my matrix or of my transformation. So we've said in an earlier video that the codomain represents all potential outputs. So if I am going to get an output, it has to be inside of Rm. But that does not necessarily mean that I'm going to get everything in Rm as an output. Like in this picture, I only got the things in red as outputs. I only actually achieved the things in red. And that's what the range is. The range is all the outputs that I actually achieve, that I actually land on. So in general, these two things are not always equal. And we've seen that before in an earlier video of this section. But when they are equal, when the codomain and the range are the same, we call our function, or we call our matrix, onto. So I want to state that definition. Okay, so the definition is, it says that our transformation is onto if and only if the range equals all of Rm. Or in other words, so i.e., this is saying if the range equals the codomain. So in my picture, if this red area had filled out all of Rm, if the range was all of Rm, then we say the function is onto. Okay, so let's box that. So I'd like a way to be able to determine when a transformation is going to be onto. So that's the next thing that I want to state. Okay, so function is on when the range, based off of what we're saying here, when the range equals Rn. Okay, and now let's scroll upwards a little bit. Let's zoom out. What was the range? A little bit more. The range is the span of A1 up until AN. Okay, so we need the span of A1, comma, dot, 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 up until AN to be equal to all of Rm. Okay, so let's zoom back in on this. Okay, so when does this happen? When does the span of a bunch of vectors equal all of Rm? So that we have seen before. This happens if and only if, when we form an augmented matrix with A augmented with B, if this is consistent for all vectors B. So that we have seen before. And when does that happen? When is this augmented matrix going to be consistent no matter what B is? Well, that happens if and only if. At this point, pause the video and think about this for 30 seconds. When does that happen? When is this augmented matrix going to be consistent for all vectors B? So 4, 3, 2, 1, pause the video. Pause the video and think about this for 30 seconds. Okay, so hopefully you guys have done that. So this happens if and only if A has pivots in each row. In each row. That's what I need. And I'm coloring this in green because in practice, this is how I check if a function is onto. I look at its matrix and I see if that matrix has a pivot in each row. Okay, so let's box this as well. Okay, so conceptually, when there's a pivot in each row, the range in my picture is going to be large enough so it fills up the whole codomain. And that's when my function is onto. Okay, so next let's define another term called one-to-one. Okay, so I'm going to begin by stating the definition, and then I'll explain conceptually what this means. So a transformation T sub A is one-to-one if and only if when T of U equals T of V. That implies that then the vectors U and V are the same. Okay, so what does this mean? The easiest way to break down what this portion right here is saying is to look at what's called the contrapositive. This is something that maybe you guys remember. This is something that sometimes is introduced to us maybe in geometry class. But if I have an if-then statement that says something like, oh, if P, then Q, so that's my original statement. The contrapositive, I'm just going to call it CP for contrapositive, is if not Q, then not P. So it switches the order of these two things, and then it negates both of them. It says, it puts a not in front of both of them. But it turns out that these two things are equivalent to each other. Okay, so let's state the contrapositive of this statement right here. So we'd be saying if the conclusion is not true, so that's if U and V are different, if they're different vectors, then the given is not true. So T of U is not going to be equal to T of V. Okay, so let's box this definition. So I know this may still be a bit abstract, so let's draw a picture to help us visualize what this is saying. It's easiest for me to explain what something looks like if it's not one-to-one. First, so not one-to-one. What does something look like if it's not one-to-one? If it does not satisfy this property. Okay, so I'm going to draw a circle to represent my domain, to represent Rn. And I'll draw a circle, an oval technically, I guess, to represent the codomain, Rn. So something is not one-to-one if I have two vectors in the domain. Let's call them U and V, just like I'm using. That, when I plug them into my linear transformation, I get the same thing out. So if T of U equaled T of V, that would be bad. And that's all about what the contrapositive is saying. It's saying, oh, if I have two vectors that are in the domain, like U and V, that are different, that are not equal, then their outputs, T of U and T of V, better be different. But in this picture, that didn't happen. These two inputs, U and V, had the same output. So that's when my function is not one-to-one. For my function to be one-to-one, no matter anytime I take two different inputs, I need the outputs to be different. And that did not happen here. Okay. So now, let's try to state a rule to determine if a transformation is one-to-one or not. Okay, so the first thing that I'm going to say is, so a transformation is one-to-one if and only if when an augmented matrix, A augmented with B, so if that augmented matrix is consistent, there are how many solutions? So if this augmented matrix was consistent, there is a unique solution. Because if there wasn't a unique solution, that would sort of correspond to a picture like this. Like if I had two different inputs that gave me the same thing out, I wouldn't have a unique solution. I'd have more than one. And then my transformation would not be one-to-one. So for my transformation to be one-to-one, whenever this system, this augmented matrix is consistent, there has to be a unique solution. Okay, and when does that happen? So this we have a better feel for. There is a unique solution. What does that mean? That means the reduced matrix A has a pivot in each column. And actually, let me go ahead and write this in green so it shows up a little better. Okay, so I went ahead and did that just to save a little bit of time. So if there's a unique solution, that means there's no free variables. So then my matrix has to have a pivot in each column. And I've put this in green because in practice, this is how we check if a transformation is one-to-one. We look at its corresponding matrix, its standard matrix. You row reduce it and see if there's a pivot in each column. And if there is, it's one-to-one. And just for a little bit of review, we know what this means. We learned a definition for what it means if there's a pivot in each column. That means the columns A1, comma, up until AN are linearly independent. So I'm just going to write Li. Li refers to linearly independent. Okay, so let's box this. So next, let's look at an example. Okay, so I'm going to end the video with this. Okay, so let's let A be this matrix. And I want to know, is the linear transformation that's associated with A onto? And is that linear transformation that's associated with A one-to-one? Okay, so how do we solve this? Okay, so what I need to do is I need to take my matrix. So 1, 3, 5 in the first row, 2, 4, 6 in the next. I need to row reduce it and see if there's a pivot in each row, and then see if there's a pivot in each column. Okay, so I want to make this 2 become a 0. So I need to do negative 2 times row 1, add it to row 2, and insert that into row 2. So doing that, my first row stays the same as 1, 3, 5. But the second row becomes 0, then I get negative 6 plus 4, negative 2. Then I get negative 10 plus 6, which is negative 4. And at this point, I see the pivots. I know this 1 is a pivot. Let's put it as a box, actually. That's a pivot. This negative 2 is a pivot. So those are the pivots. Okay, so we see that there are pivots in each row. And when there are pivots in each row, our matrix, or our transformation, is onto. So TA is onto. So are there pivots in each column? So no, because the third column doesn't have a pivot. So not all columns have pivots. So if not all the columns have pivots, that means our matrix or our transformation is not one-to-one. It's not going to be one-to-one. And that is our answer.